Hello everybody, this is Miss Woods here with you again. Today we're going to be reviewing redox reactions, and just a disclaimer, this will be one of the longer videos that I post for you to watch because, redox is a hard topic. Students struggle with it, right? So I just want to make sure that I am giving it as much attention as it deserves. So by the end of this video, you should be able to describe how electrons are transferred in a redox reaction and write an oxidation half reaction and a reduction half reaction. Get out some paper, write down what you feel like you need to write down, right? These are your notes. You are an independent learner now, so do what's best for you, okay? So, if we move on down, right, let's just talk a little bit about what redox reactions are. So, redox reactions is just another name for a single replacement reaction. So aka single replacement. Okay. So redox is the better name for it though, because it is really telling us how the reaction is taking place and what is happening as the reaction takes place. So if we break down redox, right? Redox is just a combination of oxidation and reduction. So oxidation is when electrons are lost, and reduction is when electrons are gained. Right? And that sounds kind of weird, right? When you think of something being reduced, you don't think about something being gained. But if you think about electrons, right, we know that electrons have this negative charge. So if an atom is gaining this negative particle here, then the charge is reduced. Okay, so charge is reduced. Wow, that is terrible handwriting. Let me try that again. Charge is reduced. Alright, cool. That looks a little bit better. So, that means if a atom is losing electrons, right, in oxidation, right, this charge is increased. So charge is increased. Okay, so cool. Let's go over a little acronym to help you remember oxidation versus reduction, right? I like to use oil rig. You might hear Leo Gur or Leo the lion says Gur. Those are the dumb acronyms, right? The way to go is definitely oil rig. So, the oil part, right? The O is oxidation. So oxidation. The I is, and then the L is loss of electrons. Okay, so then you could probably guess the rig part, but the R stands for reduction. And then the I still is, and then the G is gain of electrons. Okay, so just a little acronym to help you out as we move forward writing these half reactions. So there are a couple steps that I want you to keep in mind before we start writing these half reactions. So you always want to make sure that the reaction actually occurs. So we talked about this in the last video. Since redox reactions are just single replacement reactions, right, we use the activity series to determine if the reaction occurs. Right? If you skip this step, you might be writing a half reaction when you don't even have to. So, step 2 then, make sure your equation is balanced to start. Not every teacher does it this way, but I do think this is the easiest way to do it. And then next you want to identify the charge of each chemical species before a reaction and after the reaction. And then our last thing to keep in mind as we do these half reactions is when electrons are lost, right? So when an atom is being oxidized, we want to treat those electrons as a product, right? Versus when an electron is being gained, we want to treat that as a reactant, right? Because the atom or ion is actually taking in those electrons, right? So it's two things actually combining together. So let's try our first example, right? So here I have lithium reacting with copper 2 sulfate to form copper and lithium sulfate, right? So like I said previously, right, step 1, always make sure this reaction actually occurs. So if you guys remember from the last video, right, the single element here is going to try to swap places with copper, right? Usually when two things are swapping places, it's the two metals in a single replacement reaction, right? So since lithium is the higher element on the activity series, right, and copper is way down here, the single element has to be higher on the activity series, so lithium is higher, so this reaction does occur, so we are good to move forward. So let me erase this just to give us some space so it doesn't get messy. But my second step was make sure we have a balanced chemical equation. Just looking at this right now, I can see I have one lithium on the reactant side, right, or the left side, but I have two lithiums on the product side or the right side. So that's already showing me that this is not balanced. So I'm going to go ahead and put a little 2 right in front of the lithium there. And everything else is balanced then. So we are good to go. So step 3, I said identify the charge of each chemical species before the reaction and after the reaction. So here, we'll just go in order of how they appear. So lithium, all by itself, not chemically bonded to anything. When an element is not, or an atom is not bonded to anything, that means that it's a neutral charge, right? So the charge of this lithium atom right here is 0. Okay. So now copper, in the copper 2 sulfate, this element is a D block metal or a transition metal, so we cannot get its charge just based off of its location on the periodic table. So I have to determine its charge based on the thing that it's bonded to. So sulfate, right, has a -2 charge, and I know that copper has to be able to cancel out that -2, so that's going to make copper a +2. Okay, so that is my reactants in each one of their charges. And then so on the product side, copper is now all by itself, right? Not chemically bonded to anything, so copper is going to have a neutral charge now. And now lithium is ionically bonded to sulfate, but lithium is in the group 1, or it is in group 1, and all of those metals have a +1 charge no matter what. Right? Lithium will always form that +1 charge. So I'll put +1 there. And sulfate is still -2. Right? And if you guys can see, right, even though I had 2 lithiums, that did not affect lithium's charge, right? It's just saying that I have 2 lithium +1 ions, okay? So keep that in mind as we move forward. So, we are ready to start writing our half reactions then. So if you guys remember the acronym oil rig, right? Oxidation is loss. We want to identify which species has lost electrons. And remember, if you're losing this negative particle, the thing is going to become more positive. So we got to look which one of our species is becoming more positive as the reaction takes place. Right? So if I look, lithium starts with a 0 charge, but then it changes to a +1 charge, right? So that's telling me that electrons were lost in this situation, or in this reaction. So I'm going to write lithium, or focus on lithium for my oxidation. Lithium starts out as a neutral atom, but then it turns into a lithium +1 ion. Right, so you can see that as it moves from 0 to +1, that means only 1 electron was lost. And if you remember from my previous slide, I said if electrons are being lost, treat them as a product. So since we went from 0 to +1 and 1 electron was lost, I'm going to say +1 electron here. Right, so this might be where I might do it differently. than your teacher. I guess it just depends on what you have or who you have as a teacher. Neither one is right or wrong, right? This is just the way I like to do it. I had these coefficients up here, right? I had two lithium atoms to start, right? And then on my product side, I also had two of these lithium +1 atoms, or ions. So I'm going to put a 2 there as well. So when I'm putting this 2 in front, I'm saying that this reaction is taking place twice, right? A neutral lithium atom turns to a lithium +1 ion 2 times. So that means total, right? I'm going to erase this. That means total I'm going to have 2 electrons being lost in this situation, okay? So that is the oxidation half reaction, right? Not too bad. So let's do the reduction one, right? So remember, reduction means a element or ion is gaining electrons. So I got to figure out which thing is gaining electrons. Remember, the charge is going to be reduced this time, right? It's going to decrease. So if I look, right, I can see that copper starts out as a +2 charge, and then it turns to a neutral atom, right? No charge at all. So that is a decrease in the charge. So that means the copper ion is being reduced. So if I were to write this, right, copper on this side starts out as copper 2+. Okay, copper 2+. And it turns into, on the product side, a neutral copper atom, right? I don't have any coefficients for these coppers, or I only have one of them, so I don't need to do anything with that. But since we went from +2 to 0, that means 2 electrons were lost, right? That difference between +2 and 0 is 2. So 2 electrons, were gained. So I am going to say +2 electrons. Because remember, from my previous slide, I said if electrons are being gained, treat them as a reactant. So this is basically saying that copper is taking in those 2 electrons to make a neutral copper atom. Okay? So those are our half reactions. They are not too bad. Just an important thing to remember as we move forward with the net ionic equation. These electrons here and here, right, they should be equal. Okay, so that's why I like to bring down the coefficients from the original balanced equation, because when you do that, you're always going to have an equal amount of electrons transferred. Whereas if you don't bring down those coefficients, you're going to have to do it later on anyways. So I think it's better to start off with that, okay? So for our net ionic equation then, right, we're basically just combining the oxidation half reaction and the oxidation half reaction. Or sorry, the reduction half reaction and the oxidation half reaction. So, you guys can see, right, I have 2 electrons on my product side and 2 electrons on my reactant side. So when something appears on the reactant side and the product side, it cancels out, right? So it just kind of goes away. So there's nothing else that appears in the same form on both sides of the equation. So now I can start combining these 2 reactions together. So on the reactant side, right, I have those 2 species. So I'm going to say 2 lithium atoms plus a copper 2+ ion, right? And then on my product side here, right, I have 2 lithium +1 ions plus a neutral copper atom. Okay, and that's it. This is our net ionic equation, right? So hopefully you're okay right now and you're not feeling too bad about it. While I'm talking, if you have questions, go ahead and write them down, and you can always ask me later. So, these, we can write these half reactions all day, but if you don't really truly understand what's happening, then there's no point, right? You're not getting the purpose of this reaction. or understanding what's happening in this reaction. So if I look at my oxidation and reduction half reactions and kind of put it in a model for you all. So you can see here, right, to start, I have 2 neutral lithium atoms and only 1 copper 2+ ion, right, which is what I have shown on this side here. Okay, so keeping the amount of each one of these atoms or ions correct, right, 2 to 1. So, you know, lithium changes from 0 to +1, right? So if you think about it, how many electrons does that lithium atom lose? Right? Hopefully you think about it and you say 1, right? So this lithium atom here is losing 1 electron, and this lithium atom here is losing 1 electron, right? So 2 electrons total, okay? But where in the heck do those electrons go? Well, if you guys look right here, right, it says that a copper 2+ ion is gaining those 2 electrons, right? So this electron that lithium lost, right, is going to go to the copper, and then the electron that this lithium atom lost is also going to go to the copper ion, okay? So then in the end, right, now I have 2 lithium +1 ions and 1 copper atom. Right, so that is just our exchange of electrons there. So hopefully that clears this up for you guys a little bit. So why don't you guys go ahead and pause the video and try this next reaction on your own, right? Give me the oxidation, reduction, and net ionic equation, and then hit play when you're ready to go over it. Alright, so let's see how you did. So first step, we got to make sure that this reaction even occurs. So I need to make sure that tin is higher than silver, right? Because that single element has to be higher up than the thing that it's replacing. So we have tin right here and silver down here. So since tin is higher, this reaction does occur. So we are good to go. So next step, make sure that it's balanced. So I can see that I have 4 nitrates on this side, but only 1 nitrate on the reactant side, right? So that's not balanced. So I need to put a 4 in front of this one to give me 4 nitrates. But when I put this 4 in front, that also affects the silver. So silver here on this side also has to be 4, right? And now we have a balanced equation. So in order to write our oxidation and reduction half reactions, we have to look at the charges, right? So maybe we have tin all by itself on the reactant side, right? Not bonded to anything. So that charge is going to be 0. Okay? So on this side here, right, silver again is a transition metal located in the D block, so we have to determine its charge based on the thing that it is bonded to. So nitrate, hopefully you have this one memorized as well, has a -1 charge. So in order for silver to cancel out that -1 charge, it has to be +1. And just a little secret for you guys, silver always has a +1 charge. It's one of the few transition metals that don't form multiple charges. So it's just something to keep in mind. And remember, even though I have 4 silver +1 ions here, I didn't change the charge to be +4, right? Each silver ion has a +1 charge, and I just happen to have 4 of them, okay? So I have my reactant side done in terms of determining the charge. So now let me determine the charges of my other chemical species on the other side, right? So now silver is all alone, not bonded to anything, so that's going to have a charge of 0, right? Tin, again, D block transition metal, so I have to look at the charge of nitrate. So nitrate has a -1 charge, right? But you can see it took 4 of them to cancel out the charge of 10, right? So I have a -1 times 4, right, gives me -4. So that means that 10 has to be a +4 charge, right? So hopefully you remember doing that when we were learning how to write formulas to determine that charge. All right, so oxidation, right? Electrons are being lost, which means the charge gets bigger. So let's see whose charge gets bigger as the reaction goes on, right? And I could see that 10 starts as a 0 charge and changes to a +4, right? So that increase in the charge is telling me that 10 lost electrons. So I'm going to start with how 10 appears on the reactant side. So I have Sn, right, with that little 0 there. And guys, you don't have to include the 0. I just like to do it to say that it's a neutral charge, but if you don't have it, it's not a big deal. And then on the product side, 10 turns into Sn with a +4 charge, okay? So since it went from 0, right, to +4, right, that means that 4 electrons were lost in this. So I'm going to say +4 electrons. Okay, so if you got that right, very nice job. If you got it wrong, hopefully you see where you went wrong, okay? And you can always try again if you need to. So, for our reduction one, right, electrons are being gained, which means the charge is being reduced. So, let's see, which species is being reduced? So, silver goes from +1 to 0, so that charge went down. So silver is my species that has been reduced. So I am going to say that I started off with Ag with a +1 charge, and by the end of this, right, it turns into a neutral silver atom, right? So going from +1 to 0, right, if you guys see that, the charge, right, that means only 1 electron was lost. So remember, if we're 1 electron was gained. So if we're gaining 1 electron, I'm going to put that on the reactant side. So remember what I told you, right? The number of electrons lost and gained needs to be equal. So if you guys remember from the last example, I brought down coefficients to make that happen, right? So I have 4 Ag +1 ions, and I have 4 neutral silver atoms, right? So when I put that 4 there, that also is going to, let me just do it this way, right? Allow me to make that a 4. It looks bad. Let me just erase it. Okay. So now I could say +4 electrons, right? Because a silver ion going from +1 to a silver silver neutral atom is happening 4 times, right? So +1 to 0 4 times, right? So that gives me 4 total electrons being transferred, right? So now our number of electrons lost and gained are equal. Okay, so when we write the net ionic equation here, right, again, I am combining my oxidation and reduction half reactions. So I have my electrons appearing on both sides of the equation in the exact same form. So those cancel out. So I am left with these 2 species on my reactant side. So Sn with a little neutral charge plus 4 Ag +1. Okay, and then I am left with these guys as my products. So Sn with a +4 charge plus 4 neutral silver atoms. Okay, so that's the net ionic equation there. So one thing I forgot to mention earlier, if you notice, I haven't done anything with the nitrate, right? If I go back up here, nitrate was in the equation, but if you notice, right, nitrate's charge has not changed, right, from beginning to end. It's just there, right? When the charge isn't changing, right, that means it's not part of the reaction, and this is called a spectator ion. Right? It's just there, kind of hanging out, letting silver and tin do its thing while it just watches in the background, right? Which sounds kind of creepy, but that's what it's doing, okay? So same thing up here. Why in this drawing I didn't include the sulfate, right? So same thing. Sulfate had stayed the same charge from beginning to end, so that was a spectator ion. So I didn't feel the need to include it in the model here if it's not really part of the reaction, okay? So hopefully you feel okay with this. Remember, if I went too fast on something, you can always rewind and watch it again. But yeah, that's the end of this video. I hope it makes sense, and please let me know if you have any questions.